Hi there, we all know that large language models or LLMs are amazing when it comes to content generation. And they have been trained on massive data sets, which makes them brilliant at tasks like summarization, question answering, or email writing, and much more. But they do have a limitation. Let's say you are building a chatbot for your own company. You want your employees to ask questions like, what is the updated leave policy in this company? Now, an LLM might try to answer that, but most likely it will either hallucinate an answer, give you something very generic, or just say, I don't know. Why? Because the LLM hasn't been trained on your company's internal documents and it simply doesn't know your HR policies, right? And this is exactly where RAG comes in. Hi, I'm Anuradha and welcome back to this LangChain Complete Beginner series. You are with me in part 3 and in this lesson we are diving into one of the most exciting applications of LLMs, RAG. RAG stands for Retrieval Augmented Generation. You enhance your LLM by connecting to your own external data, whether that is your company's HR policies, products, documents, knowledge base, and this gives your chatbot superpowers. At a high level, a RAG pipeline looks like this: document ingestion, where information is extracted and prepared; information retrieval, where relevant chunks are fetched based on the query; and then the third is answer generation, where the LLMs use both the query and the retrieved chunks to generate response. So let's talk about phase 1, which is document ingestion, preparing the data. This is where we set up our data for retrieval. We start by loading the documents to build the knowledge base. LangChain provides us with a powerful tool for this, which is document loaders. Now, these loaders allow us to pull in data from all kinds of sources, be it PDFs, CSV files, databases, Jupyter Notebook, basically wherever your data lives. So LangChain helps bring it in and prepare it for further use. Next step, chunking the documents. Once the documents are loaded, they are split into smaller chunks. And why? Because the LLMs have token limit, they can't process huge documents in one go. So we split them into meaningful chunks that fit within model limits and preserve enough context to be used during retrieval. Then comes embedding. Once the documents are chunked, we need to embed them. Embeddings are numerical representations of each chunk. You can think of them as converting text into vectors, and these vectors are used to calculate similarity between the user query and stored chunks so we can retrieve the most relevant information. The resulting embeddings are then stored in vector stores or vector databases. And if all of this sounds alien and you are not familiar with what embeddings are or how vector databases work, I would suggest you to go and head back to my two amazing tutorials. One is Text Embeddings Explained, where we dive into how embeddings work using OpenAI models with hands-on example, and the other is Vector Databases Explained, where I explain vector databases in simple terms and demonstrate using ChromaDB how to use them with your application. Now let's move to the second phase of the RAG workflow, which is document retrieval. And this is where the relevant chunks are extracted from the vector store based on user's query. And how does that happen? It is done using similarity search. The user's question is also embedded and then compared to the document embedding stored in the vector store, and the closest match is returned, which is the most relevant document chunk or chunks are retrieved, they are returned. Finally, we reach the third phase, which is answer generation by LLM. So let's do one thing, let's walk through what happens end to end once the user submits a question. And this is where we will use the LangChain expression language, LCEL, which we have already explored in our previous lesson. And let's see how whole system retrieval plus answering works in LangChain. So the user question is passed into the retrieval chain. The chain has two parts. First, the retriever pulls relevant document from the vector store, and the retrieved chunks are assigned to a variable called context. Next, the original question is passed through using a component called runnable pass-through, and this is simply forwarding the question unchanged, letting it to be used later in the chain. Now both the question and the retrieve context are combined inside a prompt template, something we have already covered earlier. This prompt, question plus context, is sent to the LLM, which then generates the answer. And finally, the output from the model is parsed using an output parser, converting the response into a readable format, let's say string. And now it's the time to action. Let's head to Jupyter Notebook and put all this together. And here's what we will be doing step by step. We will be loading a sample company policy document. We will be chunking and embedding the text, store the embeddings in ChromaDB, and we will be creating a retrieval chain using a retriever LCEL component, prompt template, LLM, and by the end of this lesson, you would have built your own working first RAG application. Quite excited about it. Let's keep on moving and let's head to Jupyter Notebook. So in the first lesson of this series, we set up our LangChain environment and learned how to load our OpenAI key and define an LLM using LangChain. We also explored how to interact with the model through LangChain itself. And now to continue further in this lesson, we will simply duplicate this initial script. Along with that, we will upload a sample HR document. I have taken this from a publicly available source, and it contains various policies, including the leave policy. We will use this document as a base for building our RAG application, asking a question about the leave policy and making sure the answer is retrieved from within this PDF. So make sure this file is uploaded in your project folder, and you can grab it directly from my GitHub repo. The link is given in the description. So let's continue from there. I'll rename this script with the get started with RAG. All right. So here we have already loaded OpenAI key, which is available in our environment file. We have defined model, but we will be defining different embedding model over here. I'll just remove this sending first request. We don't need it over here. Send second request. And what we will be beginning over here is the document ingestion part first. Now the document ingestion or the knowledge preparation phase and the indexing phase begins with the document loader component of LangChain. We have a PDF. We will be using PDF loader. Let's just have a look at what are the different document loaders. I'll go to LangChain page for that. There you will see we can upload from a web page, then we can also upload it from PDFs. We can upload it from AWS S3 bucket. So many options, social platforms, messaging services. And let's have a look at PDF loader. It is used to load and parse PDFs. So right now our data is residing in sample HR manual, which is a PDF. So we will be using PDF loader for implementing PDF loader. So if you go over here in PDF, we need to install this package, and also we need to have LangChain community, which we already have. So we'll just install PDF. Mine is already installed, but simply I'll add the line over here, pip install PDF. So that is what you have to follow over here. Now we have to import the wrapper from LangChain community document loader to interact with this PDF. So this PDF loader, we can load and parse our PDF document So let's create the instance. So we'll just copy this, and to this we will pass the path of our document, which is currently present in the present path itself. Then we will create a document instance equal to loader.load. Let's see what this document contains. So if you will see, this document itself has 11 pages, right? And if we go over here, so if we go over here and we check, the document is a list, right? And let's see the length of this list. It has got 11 elements in it. That means every page is divided into one element for this document list. And let's say we want to see the content of one page. For example, in sample HR manual, we have leave policy on 10th page, right? So that would correspond to 9th element. If we have to go to the page content, we will access it using the element list and then the page content, and this gives us the contents of page 10 in this. And here, as you can see, leave is also mentioned. So that is how we load the PDF page using PyPDF document loader. Now let's move to the next part, which is splitting the document. So why split? First of all, because LLMs have token limit. For example, GPT-4o, for example, it has a context window of 128k tokens, but most LLMs, they operate around like 4k 16k tokens, and we cannot feed an entire 100-page document. That would definitely exceed the limit. The other thing is better retrieval in RAG to match queries, right? So let's take an example, like if someone asks about a specific policy in a 200-page HR manual, if we give them just the relevant paragraph, they will answer fast, right? So what is happening in RAG is we are retrieving the relevant chunk on the basis of similarity and then finding out the answer to the query. So first chunking is needed, that is splitting is needed, so that relevant chunks can be extracted. So let's move to the next step, which is splitting the document. Now to split the document, let's go to text splitter page of LangChain, and you will definitely get a good insight if you have a look at this page about the concept, and it also tells about how we can split a document, and maybe length based, where we are specifying the number of tokens which can be there, or character based, splitting on particular character like paragraph, next line, dot, right? Then there could be text structure based, which is like upper form of character based, but giving characters hierarchy, keeping the chunk size into consideration. We'll just see it recursively checking different characters while giving importance to chunk size. When we will look at it, we will see that there are two primary parameters, chunk size and chunk overlap. Chunk size refers to the number of characters, maximum number of characters that should be within the chunk. This is not exact, but this is the maximum number of character while considering the split at particular character. We will just see that. And again, there are others also, like document structure based, semantic meaning based. We will just looking into two for now, character splitter and cursive character splitter. First of all, you need to install LangChain text splitter for it, and we have already installed as part of our environment setup, and it is also available in our requirement.txt. So before we split into this document, let's take a simple example to understand how character splitter and recursive character splitter differs. So let's say we have a simple text, hello world, my name is Anuradha, and these are very small sentences separated by dot, and then there is a long sentence. Now let's say for splitting, we will import character text splitter and recursive character text splitter. Now to form we will first create the instance of character text splitter, And let's say we want to split our text at dot, and we specify that when you meet the maximum size of 25, even this dot is not met, just break it. Okay, and chunk overlap we will just see in some time. So let's have a look at this. There is a default separator also, which is, I guess, paragraph character /n/n. So anyways, we split our text using character splitter instance which we have created. If we see what is inside the character chunk, we will find something like this: hello world, because there was a dot after that, so it disconnected it over here. Mind that maximum chunk size is 25. Then my name is Anuradha, chunk size remains within the limit. I teach data science, within the limit. But when it comes to the long sentence, LangChain is where this dot is appearing after the coverage of 25 chunks. This splitter, the character text splitter, is not giving importance to that. It is just giving importance to the character mentioned. And apart from that, there is, if you will see, there is no overlap really happening over here. What by overlap we would have meant is one chunk ending and the other chunk beginning have some overlap of text so that the context can be maintained. Now here, if we move to the other character splitter, which is recursive character splitter, it has by default separators, so it will definitely respect chunk size, and if this character is not met and chunk size has already met, it will fall back to the next character. So how it happens? So similarly, we created a chunk size over here and we have a chunk overlap. So if we will print the chunks over here, perfect. Hello world, my name is Anuradha is 1, because we have given dot over here and the chunk size is 75, right? Let me give chunk size of 25 over here, 5. All right. So again, yeah, hello world, my name is Anuradha, teach data science, perfect. So first thing is the character overlap over here in data, right? LangChain is a powerful framework that helps build LLM applications. So it is definitely respecting the characters and keeping the limit within the chunk size, first thing. Now what character separators we need to give? We need to give according to the document, right? So in our document we feel that first priority should be given to the paragraph. What we want is chunk should be containing at least one context, and that is our judgment, right? So in case of document, what we can do, we can add the first priority splitter is, let's say, paragraph. Okay, so let's say I give /n/n, or then the line. If /n/n does not fit within chunks, then we can move to, let's say, paragraph has more number of chunk, more than chunk size, then we can fall back to next line. And then instead of split text, we will do split documents, right? And here it is, our document is HR manual, which is a list of pages. And let's see, when we do the same thing, we get this whole. So as you can see, it divides the chunks, this whole pages into chunks, right? And if we have given the chunk size of 400, and if we go over here, the limit is maintained. And now the time somewhere here lies in these chunks of 400 size, the leave policy. And in our next action, what we will be doing, we have already talked about how embedding works, how vector store works in one of our previous lessons, which I have also mentioned here in description. You can visit it if you are not clear about embedding and vector stores. Now we will be moving to the third part of information extraction or document ingestion, which is embedding. So from previous step, we have generated total of 60 chunks from the sample HR manual, and in RAG pipeline we saw that we need to store external knowledge in the form of embeddings, which is a numerical representation of text, so that we can retrieve relevant chunks at query time. We will be creating these embeddings using embedding model like text embedding 3 small from OpenAI. So let's do it step by step, and we will be using ChromaDB store as well. So first, in one of our tutorial, we saw that to make use of ChromaDB, we need to install ChromaDB, right? And but in that tutorial we imported ChromaDB and we directly made a use of it. Now we are using LangChain, so of course you need to install ChromaDB, and then we need to make use of wrapper. We will be accessing Chroma via LangChain. Let's make use of Chroma using LangChain. Chroma, first part, import Chroma from vector store. LangChain is a wrapper around ChromaDB for storing and searching vector data. And then the second part is OpenAI embedding, where embedding model class for converting text into vector using OpenAI embedding AI API. Next we can create embedding model using this OpenAI embeddings, and there we can pass this text embedding small model. This embedding model will take the text as input, that is document chunks. It will return for each document a high dimensional vector. For this case of text embedding small, it is 1536 dimension, basically supposed to capture the semantic meaning of the text. And we will also be giving OpenAI key, which we have already defined on the top of this script. Now as a next step, let's load and embed document into Chroma vector store. So for that, what we will do, we will create a variable called vector store, and we will use Chroma wrapper to access ChromaDB. We will use from documents. So from documents will basically loop through each chunk which we are supplying as part of documents argument over here. We have already got 60 chunks as part of splitting, and then we have already created embedding model. So this is another argument which we are giving to ChromaDB, and then there is another argument which, let's write it first, which is persist directory equal to, let's supply some directory in the current path. Persist underscore directory, as a name says, is meant to persist the existence of embedded data on the specified folder, and if it is not given, the data will not exist once the script is running is over. All right, so let's run this vector underscore store. We can re-verify the number of documents embedded by fetching the collection again, which got stored in this vector store which we have created using .collection .get method, and then accessing this documents key. So it gives us 60 number of documents embedded. So this is awesome. We are done with the document ingestion part, phase 1, where we have prepared the knowledge base. We have ingested the document from the source. We have split it into chunks to maintain the context and retrieval efficiency, and then we have stored the embedded chunks into the vector Chroma store. And the next step is preparing the retrieval, and as part of that, what we will be doing, we will be creating a retriever. The job of retriever is to take a query is user question, search the vector store for most relevant documents based on the embedding, so query is also embedded, and then return those chunks to the LLM for generating a grounded answer. What we are doing as part of this line is we are creating a interface, retriever interface for this Chroma vector store, so that we can further use in chains. We are converting ChromaDB into a smart search engine that retrieves semantically similar chunks, and the criteria which we are providing are search type similarity, and there can be other options also as a part of retrieval strategy. But the next is search keyword arguments, which we have given as the 2. On the basis of similarity, the results would be returned in the order of similarity calculation, and then with the help of k is equal to 2, we are returning the top similar chunks to the query, and we can increase k if we want the model to retrieve more context. And now let's see how this retriever can be appended into the LCEL expression along with the query of the user. Now we will part retriever, and we will first create a prompt template. We have already learned to create prompt templates in our previous tutorial where I introduced prompt template, chains and parsers. So I'll just add the code over here. We are using chat prompt template over here, and as part of our prompt creation, we are first giving the relevant information to LLM so that it gets a ground for its answer. The second thing is we are supplying the variables, context and question. Now this context comes from the retriever output, right? Remember, once retriever fetches the relevant chunks, they are part of context. Here we are trying to retrieve 2 documents, 2 chunks, and they will form the context, and the question is the one which is coming from the user. So when we learned about the concepts, we learned that the prompt template is formed by context and question, which is finally passed to the LLM, and this is ultimately what powering up the LLM with the context. Earlier LLMs without LangChain didn't have context, without RAG didn't have context. They were simply having question and they were answering on the basis of trained data. But now LLMs also have a context, which is the relevant chunk which you have created from your own policy document. And now is the time to create a retrieval chain. Finally, we have a retriever, we have a prompt template, retriever to retrieve the context, which we will pass over here. We will also have a user query, which we will again pass in the prompt template. Let's first create a variable called chain, and in this chain we will pass the context. We'll come to it in some time. Let's separate it by comma. We will pass the question. We'll come to it as well in some time. So we have this chain and this question, which we will soon be generating from the retriever and the user query. For this retrieval chain, we are pipelining this information of a question and context with prompt. This prompt is passed to LLM, and then we are using parser to parse the output in the form of string using string output parser. We have already discussed about parsers in our previous tutorial. Let's just focus on how to retrieve context and question. So for that, we will be importing 2 things: runnable pass-through and runnable lambda from LangChain core. Now what are these? So let's have a look at runnable pass-through first. Okay, so we will make use of runnable pass-through, and we'll simply pass it in front of question. So what it means, runnable pass-through implies that it simply passes the input through unchanged. Whatever question user is asking, let's say what is the leave policy, the question key will simply be passed with the question user's question as it is. And the second is runnable lambda, and this is where the retrieval is happening. So let's say it takes the question, okay, user sends it to retriever. First we have to invoke the retriever based on the question. So again we will be taking the user question, sending it to the retriever and getting the top case similar documents or chunks on the basis of the question, and that will be finally stored as context. So runnable lambda is when we are not passing the input as it is, we are applying some function on it, right? Lambda function. So finally what we can write a lambda function over here. Whatever is the input, that is user question, invoke retriever, and in this whatever dictionary we are getting, we are extracting the question from that, and that is being passed to the retriever, which will again do the similarity calculation. So now we are done with the building of retrieval chain. Let's finally fetch our result for a particular question which we have been wanting since the beginning. Chain, we have created a chain, right? And we are invoking it with a question key which says, so we are passing the value of variable in this chain. Question, what is the updated leave policy here? All right, so this is our question, and this will help in retrieving the context and pass as a question. Now let's print the result. So we have already invoked the chain. We will print the result. Oh, I have to import a string output parser as well. Let me do that. Yeah, let me run this again. So I guess we have invoked the chain successfully, and let's see the result. So the result says the updated leave policy includes the following provisions: annual leave, maternity leave. All right, so and it gives some information, and I hope this information is also available in the leave policy. Let's cross check it. So it does talk about annual leave, maternity leave. It does not talk about sick leave or compassionate leave. So let's do one more thing. Let's just retrieve more documents. Maybe this will help. All right, so what I did, I increased the number of chunks, right? So now it starts talking about the other leaves as well. Since maybe our leave information is spread across chunks, and we need to have different spread criteria for chunking, let's also pass something which is not present in this document. So let's say I pass who is the Prime Minister of India. Let's see what it gives. I don't know. So we have supplied the context, and that context maybe it is not able to retrieve any context at all. So this is what we get, and with this we are done with our first RAG application. That was your quick intro to powerful RAGs, how we can bring external knowledge into our apps and make them way smarter. And trust me, we are just getting started. In the upcoming lessons, we will level this up by adding more components and customizing RAGs to fit your app perfectly. Up next, we are jumping into agents, one of the most talked about topics in 2025. Agents give your app the ability to reason, decide, and act. Super cool stuff. So if we are enjoying the series, don't forget to like, subscribe, and hit the bell so you don't miss what's coming next. I'll see you in the next lesson.